it could be that all the 6 bits are all the same, 0, 0, 0, 0, 6 zeros. Then you can say that maybe the transmitter will send this particular constellation symbol. If it is 5 zeros followed by 1, then maybe the transmitter will send this constellation symbol where my cursor is, and so on. So that way you can have a mapping whereby you will take 6 bits at a time and map them to a unique constellation point. For 16 QAM, that mapping is shown here. Now, logarithm base 2 of 16 is 4 bits. And so you take 4 bits at a time, like it is shown here. And then depending on what pattern of 4 bits it is, you transmit the corresponding constellation point. And so effectively for an M array modulation, each symbol transmits log base 2 of M number of bits. You can think of it as a container which contains those many bits. Okay, so that is the representation of the modulation scheme. Now in the engineering design, we have to be careful about certain design parameters. So remember, I had told you earlier, I had defined earlier, the transmitted energy per symbol. Do you remember what is the definition of the energy per symbol?
Amplitude square.
Distance from origin. We take distance from origin and average it for all bits.
Yeah.
Square of distance from origin.
It is, yeah, it is the square of the distance. If you just take the distance, you get square root of the energy per symbol. So you take the square of the distance, and then that will give you the energy per symbol. Now you can see that for QPSK, for 8PSK, for M-array PSK, energy per symbol is going to be all the same. And therefore, when you have a total of M different values which are all the same, if you take average, it is also going to turn out to be the same. Clearly, for other modulation schemes that are shown here, different symbols have different energies. If you want to transmit, for example, this particular symbol, 1111 of 16 APSK, you will have to spend more energy compared to, for example, if you want to transmit 1010. So then how to do the energy calculation is an example that we will now look at. And more importantly, we are going to now start thinking about the energy that we are utilizing in an average manner. The absolute values of the energies are not as critical, assuming that all the symbols are equally likely. And given that I will have to put the symbols apart from each other, it becomes kind of obvious that I will have to transmit some symbols at high energy. Like these 4 corner symbols of the 16 QAM will necessarily have a much higher energy compared to the 4 inner symbols which are shown here. So how much energy I'm putting on each individual symbol is not as important. What is important is what is the average amount of symbol energy that I'm asking. Some constellation diagrams will be energy efficient in the sense that they will be able to have M different symbols whose average energy is pretty small. And some diagrams will be not as energy efficient. Their energy per symbol on an average manner will be greater. Now, if suppose somebody is just focused on reducing the energy requirement, then what that engineer can do is it can draw this diagram, same diagram, except here I have kept the distance between the 2 points, the 2 closest points, I have kept it to be 1 unit. But this other, maybe a little enthusiastic engineer who wants to minimize the energy per symbol in an average manner, he or she may say that, no, I will reduce the energy per symbol by putting the symbols not 1 unit apart, but only 1/10 of a unit apart. So it is as if I pack this 16 symbols in a much tinier region. Instead of going from -1.5 to 1.5, that design, that engineer would design the same type of constellation with 16 square constellation points, but they will be covering only -0.15 to 0.15. Basically, the whole constellation has been compressed to a much smaller region. And so no wonder the energy per symbol requirement would go down. But what is the price that is paid if we go with that approach?
Performance decreases.
Yes, and that performance decreases. But why is that? Why do you think performance decreases?
Probability of
Precision
error
boundary is
increases.
very close to the symbol.
The distance between symbol decreases because
The error, the error in decoding will increase.
The correct detection region decreases.
Yeah, so we have said earlier that the probability at the receiver to confuse a particular transmitted symbol, let us say where my cursor is right now, to something else, maybe this one or maybe this one. The only thing it depends on is the distance between them. It is specifically given as q function of d divided by square root of 2 n naught. So you can reduce the symbol energy, but then because of that, if you end up getting higher symbol error rate, then maybe you haven't done this smartest thing that you could have done. And so what we are going to now focus on is defining the symbol energy, the constellation symbol energy in an average sense. But then we will also want to tie it with the distance that we are introducing between two consecutive symbols. Okay, so that distance is going to give us a control over the performance at the receiver. Whereas the average symbol energy calculation is going to give us a design control over what we can do at the transmitter. The transmitter obviously wants to minimize the average symbol energy. At the receiver, on the other hand, we want to increase the distance between the constellation points, which means that the transmitter should have maximized the average symbol energy. So these are again two different design goals which are kind of in tension with each other. Okay, so how to compute the average energy per symbol for this 16 form? It's pretty straightforward. All you do is you just calculate energy per symbol for each of 16 symbols and then just average it. So I'm sure you can do it yourself, but here I have done the calculation in a little detailed manner. So you will see that this 4 innermost symbols, if you calculate the distance from the origin, it is going to be 0.5. So 4 symbols are at 0.5 energy. Then if you look at this symbols where my cursor is this one, this, and this. So there are a total of 8 symbols which are on a circle. And the squared radius of that circle, you can just do Pythagoras theorem and you will figure out that it is going to be 2.5 units. 0.5 square gives you 0.25. And then the other coordinate is 1.5. So if you square it, you get 2.25. And so the sum becomes 2.5. And then the 4 symbols at the very extreme, the 4 vertices of the square, likewise, you can show that their energy is 4.5 units. And so if you do the average calculation, it turns out that the average symbol energy is 2.5. But this 2.5 is for case when the distance is 1 unit. And so if I do ES divided by 2.5, I actually get 1 unit. So I'm going to just equate it to distance. And so my distance formula becomes square root of ES divided by 2.5. And this should hold regardless of what the average symbol energy is for this particular constellation. Instead of 2.5, I can wish to make it 100. If I make it 100, then my distance becomes square root of 40. Instead of 100, if I make it 1, then the distance likewise reduces to square root of 0.4. Okay, so this is how we relate distance between constellation points, the neighboring constellation points, the minimum Euclidean distance, and the average symbol energy. By the way, who can tell me for this particular case, what will be the average energy per bit?
Sorry, here it should be ES by K.
2.5 by 16.
Can you repeat?
2.5 by 4.
16.
It
4,
should be
sorry.
ES
5
by
divided by
4.
4.
by 4.
Yes.
0.125.
The answer is 2.5 divided by 4, 0.0625. Because we are transmitting 4 bits at a time. Each symbol carries 4 bits. So bit energy becomes ES divided by 4. Okay, now assuming that all the 16 symbols are equally likely, meaning that the incoming bits are modeled as Bernoulli Q equal to 0.5 random source, then we have seen that the decision regions are going to be the perpendicular bisectors. And so this is how the decision regions look like. So what this means is that if there is a received vector in the presence of noise that falls over here, let's say, then you will say that this is the most likely symbol to have been transmitted, and you will demodulate the corresponding 4 bits, the 4 bits corresponding to this constellation. On the other hand, suppose if your constellation point falls somewhere over here, then which one will you demodulate?
The last one. At the
Bottom leftmost.
bottom.
Then you will demodulate this point. Yes, you will demodulate this point because this is the closest point compared to this point. So you can think of the decision regions for the outer symbols to be going like forever. They extend out into the infinity. Okay, now I want to emphasize here that this is again the minimum distance decoding example. And you know, maybe when you started this course, CT111, you thought that maybe this is CT course, communication engineering course. If there is one thing I wish that I am able to convey to you over this past several months, it is that the communication and machine learning or machine intelligence are like intimately connected. We human beings are intelligent because we communicate. I mean, what is the sign of intelligence for us? It is our ability to communicate. And the reason we are able to communicate is because we are, in some sense, our brains are doing this minimum distance detection all the time. And so the goal, the holy grail of machine learning is to be able to do this minimum distance decoding or minimum distance detection for a generalized case where the distance may not be as nicely specified as this Euclidean distance. And so for you to appreciate what the core, the heart of machine learning is, if you have understood this diagram, this decision region diagram, in the context of modulation schemes or earlier in the context of channel coding, then you will be able to relate to the ML algorithms very well. So why do I say that? I mean, let me give you a concrete example. Okay. One important problem of machine learning is that of computer vision or image detection. And that you would have seen today. If you download, I mean, if you today, for example, if you want to do an image search, all the web search engines allow you to do that. You can upload your image and then search on it. And then the search engine will give you the images which are similar to the image that you're transmitting. There is also another feature that many of the apps provide is you give as the input the photo of somebody, and it will fetch all the photos that you have in your computer memory of the same person. Effectively, the algorithm is doing face detection or face identification. So what is going on actually is that, you know, the faces are not going to be the same, even if it is the images are of the same person. The person may have grown older. Maybe you are giving a photo which is younger, or the person may be in the broad daylight, or person may be in under some shade, or may have different clothing, maybe wearing a hat, maybe wearing sunglasses, may have applied makeup, may not have applied makeup. There are so many varieties that somebody can look in a particular way. But our brains don't have difficulty in making an identification. You know, today after this lecture is over, you see your relative, and maybe that relative has come out from the afternoon sun, and so he or she is still wearing the eyeglasses, maybe the sunglasses. Just because that person is wearing sunglasses, you would not be having any difficulty in saying that she is my mom, or she is my sister, or he is my brother, or anything like that, right? You would be able to identify it. Such a trivial thing that that seems to us that if I tell you, you will laugh at me that it's because somebody is wearing a sunglass or a hat or something like that. It's not a big deal. To the extent, and maybe again I'm taking some time here to a non-technical thing, to the extent that now during this pandemic, I sometimes go out with a lot of face cover. I would have put on a mask, and I would have put on some type of hat, and there'll be extra glasses, maybe even the visor, that face shield and all that. So the part of my face which is actually only visible is probably my eyes and my forehead. That's pretty much it. Everything else is covered under the mask. Even then, the vegetable vendor or the grocery shop person is able to identify. See, what is happening is that my face to that person looks like all the way maybe somewhere over here. My face with all that facial covering, in some definition of distance, is far, far away from the typical face that he or she would have been familiar with. But still, they are able to identify that this is me, this is my face. And so this type of distance minimization is what our brains do all the time, and that is what today's ML systems are doing all the time. 20, 30 years ago, there were companies which kind of became quite successful, whose job was to do what is known as OCR, optical character recognition. All that they are doing is, for example, they are scanning the address written on an envelope, handwritten address. They are scanning it using some optical device, optical instrument. And so that instrument is generating optically recognized, optically determined characters. And the job of this algorithm is to take letter A and say that it is A. Now, if you think about it, that letter A is written in so many different ways by different people. Different people's handwriting are quite different. And the companies which became successful, they were able to do this essentially. They had this type of algorithm which will say that this is my actual letter A, and somebody might write that letter A as this, or somebody might write it as this, or somebody might write it like this. And I will say that all of these different strange looking patterns are nothing but the alphabet letter A. And so they were able to connect a wide variety of the handwritten symbols to the correct letter A. And where sometimes things became a little dicey is, you see the difference between O and Q is nothing but this little line. We are trained to detect this line and give a lot of importance to this line and say that no, this is not O. Because of this presence of this tiny line, it becomes Q. Now, O and Q are two different letters, but in some type of distance sense, they are very close to each other. What if somebody has some type of disease? Maybe their hand shakes a lot, and so he writes O like this. This is the way that that person writes O, and now it might be Q also. Who knows? Same thing is between P and R, right? So P and R also look very, very similar. This is P and this is R. So the job of this optical character recognizer, which is a machine learning algorithm, is to kind of distill all these subtleties. And the algorithm which works well is the one which is able to do this distance minimization in a very effective manner. It is not that our brains are 100% accurate in doing that. Right? I mean, this is an inherently ambiguous symbol that our brains receive. We are not able to tell whether this is a symbol Q written by somebody whose hand is not shaking, but just his or her handwriting is a little strange, or somebody whose hand is shaking. We can't tell that. So we are confused a lot of the times, and same way the algorithms also do get confused. But then nowadays, at least there are some reports that the AI algorithm is becoming better at recognizing the images, even better than what human eyes can do. If you want to hear an example of where our brains do get defeated in determining this type of detection boundaries. I mean, maybe the symbol is actually all the way over here, and our brains might still detect them as A. If you want to see a daily life example of that, recently I took my daughter to a doctor, and the doctor prescribed some medicine to her. And her prescription, as it is common among doctors, I don't know why, maybe if you have a friend who is studying in medical college, you might ask him or her whether as part of their 4-year or 6-year or 8-year degree program, whether they are forced to mess up their handwriting so that whenever they write prescription, it becomes this type of detection problem for the patient's brain. Okay, I'm just joking. But this is how the case was for the doctor that prescribed this medicine. After we reached back home, we spent literally, and I'm not exaggerating, we spent half an hour trying to understand what that lady doctor had written on that piece of paper. I would say that the first letter is A. A was a little bit okay to detect, but then N, and then C, and then I, all those letters were so hard to detect. We didn't know whether this particular symbol stands for I, or it stands for L, or it stands for something else. And so we couldn't figure out what the name of the medicine was. We had to call the doctor. The doctor again said the name in English. We didn't understand what she said, and so it was a failure. Then we had to again visit the office, and then we asked the receptionist that what is this? And then finally they were able to tell us. Even the pharmacist was not able to decode that that medicine name. So that is where I'm going with this. That although we will be doing CT in this course, I wish that you realize that there is an intimate connection of this topic with the machine learning. Okay, so this is the summary of the demodulator that we have just now talked about. So I will skip over this slide. But what I will now focus on is the error analysis. Okay, what is the probability of detection error? See, in the case, the example that I gave you, we were making detection errors. We couldn't decode that prescription, the medicine in that prescription. That is not the luxury that a demodulator has. The demodulator will detect a symbol and it doesn't know whether that detection is right or wrong. But if the detection is wrong, then the sequence of bits, log base 2 of m bits that the demodulator produces are going to be wrong. They are not going to be the same bits that the modulator has sent. What we want to know from a mathematical point of view, from an engineering point of view, is the probability of that happening. And so that is where we will now make use of some math. I will first give you an idea of what the math involves, and then I will say that actually we are not going to do that. We are going to take a shortcut. And that shortcut is quite elegant, actually. You will hopefully appreciate the main idea behind this, this scheme. Okay, so we have said this is our constellation. These are our constellation symbols. And suppose now if I want to determine the probability of correct decision when the transmitter has sent this symbol, for example, what I would need to do, kind of an extension of what we did earlier for the case of BPSK, is that I will have to take the conditional PDF of the received symbol. By the way, this received symbol is now not a scalar, it is a vector. It's a two-dimensional vector. So I will have to take conditional PDF of this two-dimensional vector, given that this symbol was transmitted. And that conditional PDF, I will have to integrate over the decision region for this symbol. And that will give me the probability of detecting this symbol correctly. So the question becomes, what is this conditional PDF? It has to be a two-dimensional PDF because there are two elements. Basically, we will have to specify this PDF along this plane. We can't specify it along a line anymore. For the Gaussian noise, we have seen that the PDF of 1D case looks like a bell, right? Well, I should say the Gaussian PDF looks like a bell which is sliced. You slice a bell in a vertical manner. And then what you get is this 1D Gaussian PDF. For the two-dimensional case, the PDF actually looks like a bell. It actually has now the full surface of the bell. We are not slicing it anymore. And so that PDF, we have to evaluate its area over this particular square. And that will give us the probability of correct detection when this symbol is transmitted. So that, sorry, I should have pointed to this one here. So this is the region of integration. This will give us the probability of correct symbol decision. We can do something else. We can arrive at a similar answer in a different manner, where instead of doing probability of correct symbol decision, we would evaluate probability of error when this symbol is transmitted. So who can tell me that?
1 minus.
But okay, fine. 1 minus of that. But what about the diagram? I mean, what will the area of integration look like, or the region of integration look like?
It should be the integral over the region outside this box, outside this
Yeah.
region.
Right. So it should be the probability of symbol error would be an integration over the entire 2D plane minus this square. Right? So maybe sometimes this is easier to do. So you, instead of evaluating probability of correct detection, you would evaluate probability of symbol error. But you know, this integration can be done. Okay, it is there in Joan Proekes's book. If you maybe when you take digital communication course, I think you will be taking that in your 4th or 5th semester. I don't remember. So when you take that digital communication course, maybe the professor that time will ask you to do this two-dimensional integration. But here for today, we are not going to do this. We are going to take a shortcut. And the shortcut that we are going to take is going to rely on that Q function. Essentially, there is a whole lot of mathematical complexity in doing this type of analytical derivation. But instead of that, we are going to do this alternative approach, which is called union bound. Why it is called union bound? Actually, it is called union upper bound. So why it is called union bound and why upper bound. That is something that we are going to look at now. And this approach is going to leverage our earlier observation that the pairwise probability of error is going to always be given by this formula, Q of distance between square root of 2 and 0. For 16 pom, we have already earlier defined this distance. And remember, we want to define it in terms of symbol energy, because otherwise there is not a design parameter that we are relating our performance to. And that formula we have already derived earlier. And so if I plug it in, it becomes the pairwise error probability becomes Q of square root of ES divided by 5 and 0. So does it make sense why this Q of square root of ES divided by 5 and 0, where it came from? Do you understand this?
Yes, sir.
Okay, so at least Somin understands it. I hope others are also able to relate these two observations that we have made earlier. And from that, we are deriving this Q function of square root of ES divided by 5 and 0. And so what we are going to do now is we are going to start painting this two-dimensional plane. But we will be painting it with brush strokes. Okay, so that is going to be the idea. Okay, so I've put all of the diagrams together, but then we'll be focusing on one at a time. So we are saying that this is the symbol that is transmitted. What is the probability that it gets mistaken as this red symbol? And that probability we have seen on the previous slide, it is Q of square root of ES divided by 5, and not because the distance between these 2 points is square root of ES divided by 2.5. But when we calculate this error probability, Q of square root of ES divided by 5 and not, we are actually, it is as if we have done integration of the two-dimensional noise-induced conditional PDF over this much belt. And this is the transmitted symbol. And when the received signal falls anywhere in this blue shaded region, it is going to be mistakenly identified as this one over here. Or it could have been identified this symbol or this symbol or this symbol. That doesn't matter. But we are actually saying that the answer of this two-dimensional double integration would be something like this. Similarly, when this symbol is transmitted and the received symbol is erroneously detected as this red colored symbol, it is as if we are doing two-dimensional integration over this belt, and so on. So that is how we keep on doing evaluation of the pairwise error probabilities. We are taking pairs of symbols at a time. What are all the nearest symbols of this green symbol? We are doing the probability that this symbol gets confused as this symbol. And now the distance between these two symbols has increased. It is now square root of 2 ES divided by 2.5. And so the formula becomes this. And so that is how we have painted the portions of this two-dimensional plane. Okay. So what we are going to do now is we are going to take a very approximate approach and say that the overall error probability, which was this shaded region, the conditional integration over this shaded region, that we are going to just say that it is going to be the sum of all of these shaded regions. The sum or the union. And that is where the word union comes. We are taking a union of all of these shaded regions. And that union is obviously going to be covering that shaded region that we had seen 2 slides ago. And so that is why this is called the union bound. It is 4 times square root of ES divided by 5 and not because there are 4 symbols. This one over here, this one, and this one, which are at a distance of ES divided by 2.5. And then the other 4 symbols, this one, this one, this one, and this one, which are little farther apart. They are square root of 2 times ES divided by 2.5. And so that is why we have 2 terms here. And both of these terms get multiplied by 4 because there are those many symbols that are nearby. And so that is where the word union comes. We are taking a union of all of these shaded regions. And this is union bound, and bound is in the sense of it's not a lower bound, it's an upper bound. Why it is an upper bound? Can somebody tell me that?
Many regions are overlapping.
Because two regions will integrate more than once.
Exactly. Ideally, we should have performed integration over that blue shaded region two slides ago. But by doing this unionization, we are kind of integrating over the same region maybe multiple times. And so the answer that we are going to get is always going to be higher than what is reality. And that is what is shown here. That the union bound is going to be above. It is an upper bound to the actual result. The red and the blue are the exact result. The red is the exact analytical result whose derivation I haven't described in this course. It's not within the scope. The blue points are the simulation, so they both are matching very well. But you will see that if I do this union bounding, at least as the SNR goes high, I get an answer which is pretty good. I mean, I get performance through that union bounding, which is close to the real performance. The real performance can never be worse than this light blue line. It is always better. Okay, so I think we have about 15 or so minutes left. So we will maybe do one more topic before we conclude. By the way, this is what I have asked you to do in your lab that was given to you yesterday. I didn't call it specifically as union bound or union upper bound, but I have given you the way to derive this type of blue upper bound line. Now, okay, before I take a pause, I take a break, I want to ask you this, and I want you to think about it, that, this is the union upper bound. There is something called improved UUB, improved union upper bound. And it comes even closer than the union bound. So maybe it looks like this. So this improved union upper bound may look like this. This is a much better, much improved approximation to the actual result. The question to you is, can you improve upon this union bounding technique? Can you think of a way by which we can improve upon union bounding technique so that we get an improved we get an improved UUB, improved union upper bound? So that is something that I ask you to think about while I take a break. Okay, so any thought on this question that I asked you?
Can we reduce
Sir, I think
yes?
If we remove overlapping region, like we do in set theory, then we can improve upon.
So what is your specific proposal? What would you do?
There should be some technique to remove the common part.
Sir, we can remove the second part of the equation. Root 2 upon 5 ES by L.
Yes, Isha, your answer I accept it. So what Isha is saying is that if I just do the 4 coloring on the top, I have already colored the 2-dimensional plane completely. I don't really need to do these other ones. See, when I do this coloring, that time all of this shaded region, this triangularly shaded region, has been already colored by one of or multiple of these 4 diagrams. So maybe this is redundant. Same way this you can show that it is redundant as well. And so we can simply remove the second part and then just keep the first part in. So the union upper bound is derived by taking a union of all the nearby symbols. The improved union bound is derived by taking union over all the nearest symbols only, not nearby. But you have to be careful that when you take all the nearest symbols, that will allow you to integrate over all the nearby symbols as well. So if I had drawn just the first part of this equation, it would have come out little better. It would have come out like this hand-drawn line that I'm showing here. And that is what actually I have asked you to do in the lab. In the lab, when you do the comparison against the bounding, you just do 4 times of Q of this function. In same way, you would notice if you look at the lab manual, for the other modulation schemes, QPSK, 8PSK and 16APSK in this lab number 8, I am asking you to do the pairwise error probability using that Q of D divided by square root of 2 and naught and just multiply it by 2. Why 2? Because for 8 PSK or for QPSK, even for 16 APSK, the nearest symbols are just two symbols, one on this side, other on the other side. And it gives a reasonable approximation to the actual simulated error probability. Okay, so now I'm going to mention one topic which is kind of important from an engineering point of view, from a design point of view, but conceptually it is lightweight. Okay, there is not some nice mathematical conceptual depth here, but still it is very important that we understand this in a clear manner. You can almost think of this as account keeping or bookkeeping. We want to know how many bits we are transmitting. We want to know how many redundant bits we are adding, let's say by channel coding. Then we want to know how many symbols we are transmitting. And we want to kind of go back and forth. How many bits each symbol is carrying, how many information bits each symbol is carrying, what is the bandwidth, what is the energy, and so on. And so that way, we can kind of translate our communication design from one metric, let's say symbol energy divided by noise power, to bit energy divided by noise power, and so on. So this is the simplified diagram of a transmitter. You have some information bit stream that might be coming out of source encoder. And let us say that the incoming bits are at some rate RB bits per second, right? Then they go through this channel encoder with a rate R, small r. And remember, R is always between 0 to 1. The output is an encoded bit stream, which goes to the modulator. And the result is some symbols sequence at some rate RS symbols per second. So let us see how to convert RS into RB or RB into RS. So first of all, we can say that the bit rate at the output of the encoder has to be RB divided by R. So I'll give you an example. Let's say RB is 1000 bits per second. And channel encoder has a rate of 0.5. When the rate is 0.5, it means that for each bit, the encoder produces 2 output bits. So obviously this RB of 1000 becomes 2000 bits per second. RB divided by R, RB divided by 0.5, and so you got 2000 bits per second. Now let us say that we are using QPSK. So we are using M equal to 4 symbols, which means that we are taking 2 bits at a time and converting them to a symbol. And so now this 2000 bits per second will become 1000 symbols per second. Essentially, RS is going to be RB divided by R, which is the input, divided by K, which is log base 2 of M. In this case, we divided 2000 by 2 to get 1000 symbols per second. So this is the final summary. Our information bit rate is RB, and our transmitted symbol rate is going to be RB divided by R times K. And this is some other example that I have worked out here. And so alternatively, you can also say that the information bit rate RB is going to be R times log base 2 of M times RS. Oh, okay, fine. So So that is all regarding this topic. I thought I had some more slides on this. We have 5 more minutes, so let us then take one more topic, which where we are going to go back to that orthogonal function representation that we did last time. And I think we also mentioned last time, the reason why we need to bring in that additional design aspect is because so far we have mostly looked at what is a very simplified model of a modulator. In real life, the system actually looks like this. So you see, we have done source encoding, we have done channel encoding, we have done the modulation. A to D converter, we are not going to do too much in this course. Maybe we might have like a half an hour session to give you a brief idea of what A to D converter would look like, but let us ignore that. But then, as you can see from this diagram, the actual system will have many other blocks. There will be what is known as frequency up conversion, which will have some reference oscillator. Then output of up converter will go through filtering and amplification. And then that is what it will get transmitted by the antenna. On the reception side, again, the antenna will get some signal. It will again go through some amplifier and filtering, and then it will go through down conversion. And then it will go through this chain that we have studied so far. So let us now focus on this. What is this frequency up conversion and down conversion blocks? Maybe this band pass filter, high powered amplifier, all of that, let us not spend time on it. But at least try to understand what this up conversion and down conversion blocks are doing. So these symbols that we have defined, let's say QPSK or 8PSK, they have to be put on what are known as sinusoidal carriers. And the purpose of this sinusoidal carrier is to allow these symbols to be transmitted in the atmosphere or over the cables. This is the entire purpose of up conversion and down conversion in frequency. If we don't do that, then either we will not be able to even transmit anything to a sufficient distance, or to be able to transmit our symbols to a sufficient distance, we will need antennas which are really, really big. There is a principle of electromagnetic transmission that as you increase the frequency of transmission, the size of the antenna that is required becomes smaller. Maybe I should write that here. Higher the radio transmission frequency, the radio frequency, the smaller is the required size of the transmit antenna. For the signal to propagate over the same distance. To reach the same distance. Signal to reach or travel Suppose if I am putting up a, I don't know, an FM radio transmitter, and I want to put this FM radio transmitter in the middle of a city, and I want to cover the entire geographical area of the city and maybe on some nearby villages. I say that, okay, I will need to make use of some antenna, some size of the antenna, maybe, I don't know, 2 meters or 3 meters in diameter. If I am using a radio frequency of maybe 1 gigahertz. But then suppose somebody tells me that, you know, instead of 1 gigahertz, you can also use 10 gigahertz. Then that will be good for me. If I am allowed to transmit at 10 gigahertz, then suddenly the size of the antenna that I need to use becomes smaller to cover the same geographical range. So that is probably the most important reason why all the modulation schemes use this electromagnetic waves. So that wavy nature of EM transmission is indicated by this symbol. This reference oscillator is generating that 1 gigahertz or 10 gigahertz electromagnetic wave in analog domain. And that is what is being emitted by the antenna. And this is the last slide for today. Stop here. So the signal that comes out of the antenna, turns out that it can be written in 3 different notations, which are all the same. They are completely equivalent. All the 3 formulas look different, but they all are equal to the same signal S of t. So this is called the quadrature notation. SI times cosine of the frequency plus or minus, this sign is not highly important, but for the consistency with these 2 equations, I have put minus sign, minus SQ times sine of 2 pi FCT. This is called the quadrature notation. By the way, you may remember from the last lecture that this is what we had studied last time. This we said it is proportional to, this was proportional to what? Does anybody remember what did we call this? Cosine of 2 pi FCT in the previous lecture?
Omega. GF
We
of
called it,
angular
G,
frequency.
G1 of t. We said that this is proportional to some function G1 of t. And this was another function proportional to G2 of t. Sine and cosine, we call them in a generalized manner as G1 and G2. And do you remember we had 2 requirements on this G1 and G2? Do you remember those?
Yes.
The integral of the
Length should be
multiplication
1.
s will be 0.
The energy of these signals over one symbol duration has to be 1, meaning there should be a unit energy waveforms. And then what was the other requirement?
The integral of the multiplication should be 0.
Right. So we wanted these 2 signals viewed in a vectorial manner to have a vector dot product of 0. And then once we take that particular interpretation, we can consider SI and SQ to be coordinates of a symbol constellation point in 2 dimensions. Now I will leave it up to you that to show that This equation here, I can also write it in a complex number format. So the constellation symbol becomes a complex number, Si plus JSQ, which J is square root of -1. And this is complex exponential of 2 pi fct. If you expand this out and take the real part of it, this means real part. So you ignore the imaginary, and the real part is same as this. You should be able to show this by writing this exponential function as cosine plus j times sine. Then you do this multiplier and then take the real part, you will get this. And the third one follows directly from the trigonometry identity. I can write this equation, the first equation, as nothing but some amplitude times cosine of 2 pi fct plus some phase. And the phase is the phase of that complex number, Si plus JSQ. And the amplitude is also the amplitude of the complex number. And so when I write it like this, the names that we had used, phase shift keying or quadrature amplitude modulation, they become clear. In phase shift keying, this A is always a constant. It doesn't convey any information. All the information is residing in the phase of this carrier waveform, electromagnetic carrier waveform, which is oscillating at some frequency f of c, maybe 1 gigahertz, maybe 10 gigahertz. In the quadrature amplitude modulation, both A and theta are changing. So this is how we will kind of convert our simplified model to a little more realistic model, which is getting transmitted over the antenna. So this is where we'll stop for today. And then when we meet again, we will continue on from this slide and see all the implications of these three notations. Okay, if you have any questions.